All right, this is Tyson again.
And this is Nathan. And we're going to be working out problem number 5, the group problems. Just pull it up really quick. So we had a few technical difficulties earlier with recording it, so we have it worked out already. We're just going to go through it with you. So in this problem, we have a person who's standing about 7 meters away from these 2 speakers that are spaced 4 meters apart, and they're directly in front of the speaker on the bottom there. We'll call that speaker 1, and the other one on top, speaker 2. The givens in this problem are that the frequency is 750 hertz, and it's important to note that those speakers are in phase. So this equation we're going to show you only works if they're in phase. And the velocity of sound is 343 meters per second.
So this equation will tell us if this position, if the observer is hearing constructive interference, destructive interference, or something in between. And when you look for M, if M is a whole number, then the interference is constructive. If it is exactly a number 0.5 with a 0.5 decimal place, then the interference is destructive. If it's neither, then it is somewhere in between. So to find delta R, we take the 2 radii, 7 meters is given. The radius to speaker 2 is given by the Pythagorean theorem, which is calculated to 8.6, and so delta R is 1.6 meters. And the wavelength is given by the velocity of the sound divided by the frequency given, and that calculates out to 4.57 meters. So when we calculate M, we get 2.3227, which is not a whole number or a number with a decimal place of 0.5.
So in that case, we're hearing neither constructive nor destructive, just something in between. So for the second part of this problem, we're asked to find how far the person would have to move towards that speaker 1 in order to hear constructive interference. So if you remember, constructive interference is a whole number. In this case, as we close in towards that speaker, our delta R is going to be getting bigger because the hypotenuse is going to only going to get a little bit shorter, and the bottom leg is going to get a lot shorter. So the next whole number up is going to be 3. So if we set M equal to 3 and plug it into our equation there, then we get that M times our wavelength is 1.37 meters, and that's equal to delta R, or R2 minus R1.
So to figure out how far we need to move, we need to set up a series of equations. So the first one is actually given here, 1.37 meters equals R2 minus R1. The second equation is just simply Pythagorean theorem. Our hypotenuse R2 squared equals R1 squared plus the other side, which is 4 squared, given from the distance right here. So when you solve for these 2 equations, it's a long algebraic process. You can also plug it into Mathematica. And when you solve for R1, you're given 5.15 meters. That's the distance between the observer's new position and speaker 1. So to find how far the observer has to move, you simply take the original position minus their new position, and you get 1.85 meters.
And that's it.